Here's a number that surprises almost everyone who's ever wired a solar setup. You can run your panels 400 feet from your battery bank and lose almost nothing in the process. If you get one decision right, get it wrong, and you can lose meaningful power over even 30 feet. The wild part is that most people never even realize which decision actually matters, because the advice floating around online is confusing at best and wrong at worst. Here's the problem everyone runs into. You're setting up an off-grid system, a cabin, a shed, a remote water pump, whatever it is, and the panels can't physically sit right next to the batteries. Maybe there's shade, maybe the roof line is wrong, maybe the batteries live somewhere sheltered and the panels need full sun somewhere else. So now you've got a run of cable between the two, and someone tells you that distance kills your power output. You go looking for answers and you find charts online showing dramatic voltage loss over long cable runs, forum posts insisting you need expensive oversized wire just to be safe, and sellers who conveniently only stock the thick, pricier gauge. It creates this vague anxiety that your whole system is going to underperform no matter what you do, and nobody quite explains why. Here's the shift in thinking that clears it up. Distance itself isn't the enemy, resistance is. And resistance in a wire is really a function of three things working together: how long the wire is, how thick it is, and how much current is actually flowing through it. Distance is only one ingredient. If you get the other two right, 400 feet of cable can behave almost identically to 4 feet of cable. This is why two people can have wildly different experiences with the same setup. One guy loses a noticeable chunk of his power, another guy loses almost nothing, and the only difference between them is wire gauge and current draw, not the tape measure. This isn't a new problem either. Long before solar panels existed, telegraph companies in the 1800s were fighting this exact battle across hundreds of miles of copper wire. And early electrical engineers had to work out precisely how much resistance a given length and thickness of wire would introduce before a signal degraded. That's actually where a lot of our modern wire gauge standards trace back to decades of real-world trial and error turned into tables that tell you, for a given length and current, exactly how thick your wire needs to be to keep losses under control. Solar off-grid setups today are just a smaller scale version of the same problem those engineers solved with copper telegraph lines. So here's the simple science behind it. Think of a wire like a garden hose. A thin hose fighting to push a lot of water through it builds up pressure loss and friction along the way. By the time the water reaches the far end, there's noticeably less push behind it. A fat hose carrying that same amount of water barely notices the distance. Electricity works the same way. Current is the water, voltage is the pressure, and wire resistance is the narrowness of the hose. The formula behind it, if you want the actual math, is voltage drop equals current multiplied by resistance. And resistance itself goes up with length and down as the wire gets thicker. So if you already know roughly how many amps your panels put out, you can calculate almost exactly how much you'll lose over any distance for any wire gauge before you even buy the cable. Now here's the part that explains why this confusion sticks around. Wire is priced by thickness, and thicker wire costs noticeably more per foot. There's a real incentive in the industry to steer people toward buying more wire than they actually need to be safe, because nobody ever complains about a system that's overbuilt. Meanwhile, panel manufacturers list two different voltage numbers on the spec sheet: open circuit voltage, which is what the panel reads when it's not under load, and voltage at maximum power, which is what it's actually delivering when it's working. Mixing those two up makes the system look like it's losing power when really someone just compared the wrong numbers. Between the upselling and the spec sheet confusion, it's easy to walk away thinking distance is the villain. You'll actually see this principle at work anywhere. Power needs to travel a long way efficiently. Utility companies step voltage up extremely high for cross-country transmission lines, specifically to keep current low and losses small, then step it back down near your house. Off-grid solar installers who run panels far from a battery shed use exactly the same logic on a tiny scale. Keep the current manageable, size the wire accordingly, and distance stops being the threat everyone assumes it is. So here's how you actually apply this to your own setup. First, find your panel's actual output current under load. Not the open circuit number, the working number, usually listed as imp or current at max power on the panel's label. Second, measure the real one-way distance your wire needs to travel, then double it, since current has to travel out and back. Third, decide how much voltage loss you're comfortable with. Most off-grid guides aim for under 2 to 3% of your system voltage. Fourth, plug your current, your total wire length, and your target loss percentage into a voltage drop calculator, which will spit out the minimum wire gauge you need. Fifth, round up one gauge size if you plan to add more panels later, since more current means more heat and more drop through the same wire. And finally, always check that your wire's ampacity rating clears your actual current with real margin, not just barely. That's a safety requirement, not a suggestion. Which brings up the limits here, because this isn't a no downside fix. Longer runs at higher current will always need meaningfully thicker wire, and there's a real point where a run gets so long, or the current gets so high, that the cost of adequate copper stops making sense, and you're better off relocating your battery bank instead. Voltage drop calculations assume steady conditions. Extra connectors, corroded terminals, undersized breakers, or aluminum wire instead of copper will all add resistance the math doesn't account for. And none of this changes the fact that oversized open circuit voltage can still damage a charge controller if you don't check your panel's specs against your controller's input rating before wiring anything at all. This is an electrical system, and getting the numbers wrong has real consequences, so when in doubt, run the calculation before you buy the cable, not after. At the end of the day, the myth here was never really about magic distance limits. It was about a hidden fact, that one overlooked spec on a wire gauge chart quietly decides whether your system performs the way it's supposed to. And that's usually how it goes with off-grid power in general. The stuff that trips people up isn't exotic engineering. It's one small, boring decision made early before anyone realizes how much it was going to matter later. That's this channel in a nutshell. Hidden Fix Lab exists to find that one boring decision before it costs you.